Good afternoon or good morning, everybody, wherever you may be. We will get started here shortly as people start to filter in. So give it just a minute or two and we'll get started. Okay, it looks like most people have joined online here that are going to join. So let's go ahead and get started. Uh, Welcome to the CAE Services Ask the MoPlo Experts series. We are doing a short series called the Back to Basics series recently. This week's topic, or this month's topic, I should say, is warpage analysis. Just a quick blurb about my company, CAE Services. We were established back in 1988. We have the most expert certified MoPlo engineers in the world. We are an Autodesk Make partner, which means we are tasked with MoPlo sales, training, mentoring, anything MoPlo related. Our consulting business, we've completed some 30,000 plus projects, and there's our website if you want to learn more about us. There's a picture of our tech center here out in the suburbs of Chicago, Illinois. This is my background, the Director of Engineering here at CAE Services. My name's Tim Lankish. My background's in physics and math. I've been here at CAE for 29 plus years. I am myself expert certified in MoPlo. I've trained 15 plus expert certified engineers over the years. I'm a trade magazine contributor and a MoPlo Summit presenter several times over. So just to recap the webinar series we've been doing here with the Back to Basics, this has been a focus on the building blocks of MoPlo analysis: filling, packing, cooling, and warpage analysis. In the first webinar, we did a little bit of an overview of the MoPlo history, what MoPlo's capabilities and benefits are. And the main message out of that one was how MoPlo allows engineers to solve problems using, solid data, right? It's not all about the software, but it's also about the engineer that runs the software, allowing that person, giving him information or her information to solve that problem, whatever it may be in plastics injection molding. Then we went on to the second webinar and talked about filling analysis and talked about how filling analysis can help us determine a solid gating scheme to do a number of things. We could avoid aesthetic problems like knit lines and so forth. It helps us develop a large processing window. Ultimately, anything we do in MoPlo, we would like to develop a large processing window so that we don't have to hit such a small target when we get that mold hung in the press as far as the process is concerned to get good results. So that's the point of a large processing window. It sets up conditions for optimal pack and optimal warp as well. Then we went on to the third webinar, which was packing analysis. And the main messages we wanted to get across with that was to get the shrinkage level right and to achieve uniform shrinkage, because the mold maker makes a couple of assumptions. Number one, they're going to pick a shrinkage level, how much shrinkage to include in the mold when they expand it. And that's oftentimes going to be based on information from the material supplier, but can also be based on mold flow analysis. But they're also assuming typically that the shrinkage is uniform. In other words, the same amount everywhere throughout that mold in all directions. Oops. And then the last webinar we did was our fourth one. We focused on cooling analysis, and there were two main focuses there. We talked about achieving cooling uniformity through proper cooling line location. If we couldn't do it that way, then maybe we would rely on cooling inserts like MoldMax or something along those lines, or using conformal cooling, 3D printed inserts to achieve uniform cooling in those difficult to reach areas. But we also focused on cooling efficiency, designing our channels and circuiting them properly so that we not only have minimal amount of flow, but we have to have turbulent flow too to extract the most amount of heat out in the least amount of time. And all of this culminates with today's webinar, and we're going to talk about the warpage basics, okay? So we'll ask the question, what is warpage? How do we know what's causing it? How do we fix or prevent it? And what if all else fails? What if we've done everything we possibly can that we know to be good in injection molding, but we still have warpage left to get out of there? What do we do? And all of those things that we've talked about leading up to now, filling, packing, and cooling, of course, have their place when it comes to determining how much warpage we can expect. Okay, so the first question we want to answer is, what is warpage? So there's really two types of deflection. When we talk about predicting deflections in mold flow, those are the results that you see, something like this. And you can see it's maybe difficult to see there, but it says deflection, all effects, X component. Okay, so whenever you're reading a mold flow report or looking at mold flow results online, have to keep in mind that you're actually looking at deflection results. And there's two types. One is in plane uniform deflection, and that results in uniform shrinkage. In other words, if I look at this one right here, we're looking at the X direction, and we see a gradual change in color across the part as we traverse the X direction. And that's just telling me that the part is shrinking uniformly. Okay, in other words, it's getting smaller and getting smaller at the same rate. That doesn't necessarily indicate warpage. When we have an out of plane non-uniform deflection, that's where we are talking about warpage. So when I see abrupt color changes, in this case, it's the Z component, so up and down in this picture, when I see abrupt color changes in that direction, say along this flange, for example, that is an indicator of warpage. So keep that in mind anytime you're looking at mold flow results. So not all deflections are warpage. Sometimes it's just the part getting smaller at a uniform rate where the part doesn't warp. So what causes this warpage? When we look at mold flow, it isolates it into four main causes. The first one being differential cooling. And that's why we want to maintain, and when we talked about in our cooling webinar, maintaining uniform cooling, because it can lead to the differential cooling effect as it becomes warpage. We have differential shrinkage. This is how the packing pressure is playing out through the mold. Areas that are packing more, areas that are packing less, lead to shrinkage variations, and those shrinkage variations, if they're large enough, can lead to warpage. We have orientation effects, and we'll talk a little bit more about that later, but essentially the material direction that is set up by the filling pattern, particularly for glass fiber filled materials, sets up variations in shrinkage that can play out in the form of warpage. Okay, so it's not just fiber filled materials that exhibit orientation effects, although those are more likely to exhibit orientation effects, but Even materials without fiber can exhibit these effects. We also have corner effects. So in the corners, when we have 90-degree type turns, or even something less than 90 degrees, the shrinkage in the thickness direction in that corner starts to matter relative to the walls that are adjacent to it. And that's what a corner effect is. Okay, so those are the four main causes. How do we fix warpage? It's going to depend on these 5 factors here: mold design, part design, material, process settings, and simulation expertise. So first we want to focus on mold design. Let's focus on filling patterns, so gate location, and a lot of this we covered in our filling webinar. Right, so here's just an example of how gate location can play out when it comes to affecting warpage. So here's 4 different examples of different filling patterns, right? All seemingly reasonable. You know, in the upper left, we're going to have some knit lines to deal with. If we don't want those, and that's off the table. Lower left, we have 2 gates on the bottom. Upper right, we have 2 gates on the top. And the lower right, we have 3 gates filling side to side. All have their advantages and disadvantages when it comes to processing. But when it comes to warpage, we can look at the fiber orientation and see how that's affected, right? I talked about how fiber orientation affects the shrinkage. So here are 4 different filling patterns that produce 4 different fiber patterns. And notice in the lower right here, we have all the fibers going in one direction. That's generally what we want to try to do when we're setting up the filling pattern for a fiber filled material. And this is how it plays out. So for unfilled materials, if we have a gate on the left side of this part, this is how the shrinkage tends to play out. Okay, the shrinkage in the flow direction tends to be greater than that in the cross flow direction. And we see the areas that are closer to the gate don't shrink as much as the areas farther from the gate. But when we go to fiber filled material, notice now we have much greater shrinkage in the cross flow direction or cross fiber direction than we do in the fiber direction. So these fibers act as little sticks. So it's not going to shrink as much in the direction of those fibers as it is cross fiber. And again, we have the effect of less shrinkage near the gate because it's seeing higher pressure than farther from the gate. So here's how it plays out. When you look at just the orientation effects, for this gating scenario, we got 13 millimeters of warp. For this one, 17, almost 18. Here we got just under 12. And even when we did everything right, we're still looking at 6.9 millimeters of warp. It's still a fair amount of warpage, you know, and this is assuming that we've got perfect cooling, et cetera. And so unfortunately, there are many times going to be cases where even though you do everything right with gating and so forth and cooling, you're still going to end up with some warpage. We also have to pay attention to the processing end of things, right? The one in the lower right was best for warpage, but the worst for processing. But as long as it's still within our processing window, then obviously we can still manage that. But look at the differences in the pressures. When we had these other scenarios, we got lower pressure, generally speaking, because we were able to reduce the flow length overall from the gate to the end of fill. And in the one on the lower right, we of course had to fill it across the part, which is the longest flow distance, and resulted in the highest pressure and therefore the highest tonnage required. But these are still well within the limits of that machine. But there are going to be cases where that may not be the case. So that's one aspect of mold design, gating, that can affect your warpage. Another aspect, of course, is cooling. And we covered this at length in our last webinar, but just wanted to show this again. And just a simple flat plate with a 5-degree temperature differential, which isn't much produced, 2/3 of a millimeter of warp here. And then when we have no differential, of course, it goes down to near zero. So things tend to bend towards the hot side. And when that's the case, we have to figure out a way to improve the cooling to reduce that warpage. And here's a case in point. And again, I brought this up in the last webinar, but we had a very tight corner here, showing some very hot spots. Initially, they didn't even have baffles in there. We put some baffles in there and we added mold max to that slide, and we were able to reduce the temperature considerably. In fact, it was even hotter than this 223 here. I think it was up at 244. So we were able to reduce it almost 100 degrees. And by doing so, we reduced the warpage in this edge here from 1.5 millimeters of warp to actually forcing the warp in an opposite direction there, just under 1/3 of a millimeter. So you see how changing the cooling alone can affect the warpage in that area. Okay, so that's mold design. Part design, of course, is also a big deal. And here's an example that I love to show all the time, but let's first talk about shrinkage-related part design issues, okay? So we see shrinkage variation across a part. If we gate on the left side of this relatively long part, we see high pressure near the gate, so we're typically going to see lower shrinkage there. And of course, near the end of fill, we're going to see lower pressure, which is going to lead to higher shrinkage. And there are some ways through processing to help reduce that variation, but again, we're looking for a large processing window, so we want to try to avoid these situations, fixing these situations through processing if we can. But that's how it generally works with shrinkage-related warpage. And here's a good example as well. This is more thickness related, but it is a shrinkage issue as well. So I just created a simple part, simple rectangular part, half of which is very thick, half of which is thin. And then I also put an even thinner rib on that thinner section there. Gated it in the middle so that we have equal flow length all the way around to each half of the mold. And you can see how this plays out, right? We have a lot more shrinkage in the thicker section than we do in the thinner section. But we have this added effect, which is also a shrinkage effect of this rib. This rib is thinner than the wall it's attached to, so it doesn't want to shrink as much. And the only way to maintain that and allow the material underneath it to shrink how it wants to is to bend it. So ribs are often a major cause of warpage in a part because of the shrinkage variation between it and the wall it attaches to. So shrinkage, or ribs rather, can be either a help in some cases when we want to try to remove warpage, or a detriment that can be the cause of excessive warpage. Here's a real world example. So the original part design was exhibiting some excessive shrinkage. Don't let this fool you. I've got that scaled up by a factor of 10 just to show the shape a little more dramatically. But they were designing a new generation of this particular part and wanted to see what they could do to help mitigate this type of warpage that they were seeing in the original mold. And one of the beautiful things about mold flow is it allows us, as we saw earlier, to separate out the different causes of warpage. So here's how much is due to cooling. You see these numbers are relatively small. Here's how much, and this is a fiber filled material, and you see the orientation effects here are also relatively small. You see a little bit there. But here are the shrinkage effects. Notice the negative number here. This is negative in the R direction, the radial direction inward. So 1.4 millimeters there. And here's the total deflection. So you look at all these and you compare them to the total deflection, which one matches the best? It's clearly the shrinkage effects. So we had to go after the shrinkage effects. And as I stated earlier, shrinkage effects are often part design related. So we looked at trying to fix this through some part design changes. One of the things we looked at was adding some stiffening ribs to try to help keep the deflection at bay. See, we're still getting some deflection here, getting some rippling in the bottom of the part. Here's another kind of a crazy idea, but just putting a little stiffening band around the middle here, this would have caused some major tooling changes. Not a good idea there. Here's an idea to remove some material, right? And we talked about how thickness affects the shrinkage variation in a part. So when we have non-uniform thickness, it leads to non-uniform shrinkage. So we tried to core out some of the material on the sidewall here, and you can see things are starting to bend in the opposite direction. So we are onto something here, but from a tooling standpoint, again, this wouldn't be real desirable. So we decided to remove material in the die draw direction. And by doing so, we were able to, again, get it to bend out in the opposite direction. And the amount that it was bending was acceptable. And now having it in this direction was also acceptable. So that's part design. We also have material issues. You know, the big one being fiber filled versus not fiber filled. And you know, those are all things that are related to the functionality of the part, right? They have to be stiff for whatever reason, taking on some sort of load. But when it comes to mold flow, we have to make sure we have good material data in order to be able to predict what's causing the warpage and attack it. And you can see right here how substituting materials in the mold flow database can give you some horrible results. You know, you look at these two right here, these are two different material decks of the same material, okay? And you can see that the filling pattern doesn't look to be a whole lot different from one to the other, but if you look at the pressure predictions, they're quite a bit different. In the one case, on the left, we have 10,450 PSI. On the right, we have 23,000 PSI. One's moldable, one's not, based on the machinery that was being used. Okay, so it's not just moldability, but this could lead to wrong warpage predictions as well. Okay, if we're predicting the wrong pressures within the part, we're not going to be able to predict the proper shrinkages. If we can't predict the proper shrinkages, then we can't do a good job of predicting the warpage. So we have to be very, very careful about minding our P's and Q's when it comes to the material that we use in simulation. It's not just this juncture loss data and pressure predictions, but it can also be the shrinkage data itself. And Moldflow uses something called CRIMS data. And in this case, you can see what happens, right? And this was an example where they ended up having to rebuild the cavity side of the tool to redo the runner system, because originally this analysis was done without CRIMS data. I'm sorry, that's on the right, and was predicting a total warp between the high point moving upward 1.5 millimeters and the low point moving down. Can't see it, but it's on this hinge point here, 1.5 millimeters. Okay, so a total warp of 3 millimeters between the two extremes. You know, after they figured out that this was warping too much, it was too late. They had built the tool, and they actually by then had CRIMS data tested, and we went back and simulated it. And if we had that data originally, 6 millimeters would have been predicted, and we would have avoided that problem. This particular customer insisted that we run this without the CRIMS data, and those were the results. So having good material data goes a long way towards getting good warpage predictions. Good warpage predictions allows us to understand what the cause of the warp is and to go attack what the primary cause is. Here's another instance of good shrinkage data. So the particular material deck that was in Moldflow at the time, this was the product of hindsight. They were building a new generation part for this and wanted to improve on the warpage. Well, the first step was to simulate what they had and see how well it was predicted. And by doing so, we noticed that we weren't predicting it well. So the material was retested, and after the testing, you can see the changes in the predicted shrinkage. So we're able to use that better data, we'll call it, to allow us to do some windage on the part. And we'll talk a little bit about windage, what it is later. But it allowed us to use that in the new generation tool to help us get a much flatter part. So that's material. It's just important to have good material data when you're trying to solve problems in mold flow. We'll talk a little bit about process settings. Again, I don't want to have to get to the point where we get warpage out of a particular tool strictly through processing. We want to try to hardwire as much of that into the part design and mold design that we can. But here's just a quick illustration of what can happen. You know, here we have a short pack time, and I see this a lot, very short pack times out at the press as for a two-shot over mold, you know, showing about 41.2 millimeters just by extending the packing time. You know, total warp came down to 5.8 millimeters. So, you know, the list goes on and on with that, whether it's filling too fast, too slow, packing too high, too low, packing too long, too short, all of those things that we've covered in filling, packing, and cooling analysis can play into the process and eventually affect the warp. But if we do our job with part design and mold design, we get a much bigger molding window, and we don't have to hit such a small target when it comes to processing. And then lastly, I'll argue that simulation expertise can play a big role here too. Expertise helps us to know when results are reasonable. We talked about material data. Haven't talked about mesh. Mesh is just creating a simulation model in mold flow, and there's different ways to do it. And with each one of those ways, they are better used in certain cases than others, okay? Mid-plane versus dual domain versus 3D meshes all have their advantages and disadvantages. And it's important to know what cases for which each of these is most beneficial. Sometimes we use more than one type of mesh on the same project. And then expertise, involves know-how, knowing how to move gates or how to improve cooling by moving water lines, knowing how to process to fix aesthetics or warpage, knowing how to change part design to fix warpage, or how to use windage to fix warpage. Here's a case in point. We'll call this the fifth cause. We talked about cooling, shrinkage, orientation, and corner effects already, but we haven't talked about buckling. And this essentially is a shrinkage effect, but it's a very drastic shrinkage effect. This was a case where there was a false positive in mold flow that was done for this customer, and then they had purchased a large amount of equipment and spent a lot of money doing it, and they tried to process this little dimple out that they were getting at the press. And after, hours upon hours and days upon days trying to fix this problem, they realized that no amount of processing was going to fix this. So they came to us and they showed us the mold flow that was done on this, and the mold flow didn't detect this buckling problem. So mold flow gets a bad name, right? No, it's not the software. It was the engineer that worked on it that didn't realize that you have to run buckling analysis sometimes, and I would argue all the time, in order to pick up these types of problems before they become a big headache. So in this case, it was a part design issue that causes the buckling. So what is buckling? Buckling is unstable warpage, where just a small additional amount of shrinkage puts it over the edge, so to speak, and then all of a sudden it just pops wildly out of place and undergoes what we call a large deflection. And this pucker here, this little dimple, is an example of that unstable warpage. It's a highly nonlinear effect, typically can't be processed out, and like I said, it's usually a design issue. In this case, they didn't really want to thicken this wall up, right? More material, etc. But after running several design iterations with different rib ribbing patterns on the back and so forth, that buckling pattern remained. So we ended up just sneaking up on this and kept increasing the wall stock until we could comfortably say that it was no longer going to buckle. So they implemented this 4mm wall. It was steel safe, right? They were able to add material by subtracting steel, and were able to get it out of that buckling mode. So big success there on that one. And then what do you do in those cases where you just can't get it out of there? And I'm not talking about buckling. You never want to do windage on a buckling case. But on those cases where, for example, that fiber-filled material that we used earlier, where there was still 6.9mm of warp left, and we couldn't get that out through any amount of processing, etc. So we use windage, or it's sometimes called Kentucky windage. And this is where you bias the mold in the opposite direction of the expected warp. So you got to make sure that all the inputs that you have are solid, right? You got to make sure that you've got good material data. That's the number one thing. But you got to make sure that you're replicating exactly what's going to be going on in that mold, or your windage predictions are likely going to be off. You would use this, as I said, when all other options have been exhausted. You can't change the material. All the gating and cooling options have been tried. You can't process it out. Any part design modifications you've tried haven't worked, or at least haven't worked to the extent that you'd like them to. So that would be a case for using Kentucky windage. So the steps to windage, and I've covered this in previous webinars in some detail, but just as a reminder, first thing to do is to make sure that the part is fees. You know, I've mentioned that a lot of issues with warpage can be solved with part design changes, and you don't necessarily need mold flow to tell you that. You know, having drastic wall thickness differences in a part, that's plastics 101, plastics design 101. You want to try to make your wall stock as uniform as you possibly can. So I've seen a lot of cases where if we had just taken a look and done a feasibility study, we could have avoided a lot of the warpage problems that we would eventually predict in mold flow. Once that's done and we've got all those design issues out, then we want to simulate mold flow and try to eliminate as much warpage as possible through conventional means, right? Part design, maybe add, subtract ribs, what have you. Changing the gating pattern, changing the cooling, all of those things we've covered. From there, we're going to determine a windage factor. How much windage do we need to put in? Is it 100%? Is it 50%? Is it 75%? We got to run that windage analysis to determine that. So we determine that shrinkage, along with that windage factor, we're going to determine the shrinkage factor, right? We have to make sure that the mold maker is going to cut the steel to the right number as well, because now, you know, when we get into this, we're going to learn that the part's going to shrink different amounts in different directions. So sometimes we need to put those different shrinkage factors into the mold to get us better results. From there, we're going to morph the CAD and we'll perform a windage check. Okay, so the morphed CAD step isn't going to necessarily match what we originally ran in a windage analysis and mold flow. Okay, so we got to perform this final windage check to make sure everything's coming back to flat as close as possible as to what we had earlier on in the process. And this morph the CAD process is something that used to be left up to mold makers, and they didn't necessarily always have the right tools or the right engineering staff to be able to do that. That's something we've been doing now for several years and have the capability of doing in-house here. So it's a nice marriage between the tooling, or the CAD morphing rather, and the mold flow analysis. We've been doing windage analysis now for upwards of 10, 15 years, and always had to rely on other people to do the morphing, but now we have that capability in-house. Here's just an example. You know, we were able to remove 15 millimeters of twist in this particular part. You know, everything was done right from a gating standpoint and processing and cooling and so forth, we got as much warp out of it as we could, but there was still 15 millimeters of warp left. You can see with all this ribbing, what a morphing nightmare that would be. So here's what the morphed CAD looks like overlaid with the original. So in yellow, we have the original, and in purple is the windage file. There's a fair amount of draft cleanup that needs to be done on morphed models oftentimes. So again, you can imagine what happens with all this ribbing, right? It looks like this in the original model. Everything's in die draw. Okay, and then we go to a windage file, and then suddenly this rib gets, bent to the side, and we have a die lock condition, right? Trapped steel on this side of the rib. Okay, one way to do it is to correct the rib draft. That's a long, laborious process, and it could add thickness to the base of the rib, or it could decrease from the thickness of the top of the rib. But there are other ways to do it where you can just leave the features in die draw. Okay, so our morphed model is now something different than what we started with previously in MoldFlow. So we have to run that windage check, as I said before. Okay, so that's windage. It can be a process, but it's a good one, and we refined it to the point where we're able to do it relatively efficiently. Okay, so just a summary of the warpage basics. What is warpage? It's an out-of-plane deflection caused by several things, mostly non-uniform shrinkage. How do we know what's causing it? We simulated a MoldFlow to isolate the cause, whether it's corner effects or cooling effects or differential shrinkage effects or orientation effects causing other shrinkage effects. How do we fix it or prevent it? We attack the predominant cause, right? And we want to try to hardwire it into the part and mold design wherever possible. And I can't emphasize that enough. Go back to the part and mold design to try to attack that predominant cause. If it's a shrinkage issue, look at making more uniform wall stock. If it's an orientation issue, look at changing your filling pattern. Those are ways to hardwire. We don't want to have to try to rely on processing if we can avoid it. And then what if all else fails? We use the Kentucky windage approach. So those are the warpage basics. They all relate back to the filling basics, the packing basics, the cooling basics, part design basics. All of it goes into what causes warpage. And it can be managed if everything is done properly. Okay, so what's new at CAE? Hope to see you guys out at the PT Expo out in the suburbs of Chicago, March 28th to 30th of next week. We're at booth 132, so if you're around, stop by, say hi. We're working on doing stress analysis, FEA, for mold, so for mold cracking, that sort of thing. That can be a big issue. You don't want a multi-$100,000 boat anchor on your hands if you are stressing a core or something so much and it fatigues and then starts cracking, and all sorts of problems result from that, right? Very expensive problem to have. So doing stress analysis on molds, using pressure predictions from MoldFlow to help do that. We are working on making that another service that we provide. I welcomed Justin last time, but for those of you who haven't seen this, Justin Bertovic is a new account representative for us. Justin has a wealth of knowledge coming from the hot runner world. So welcome, Justin. Our Autodesk partnership isn't so new, but I did want to mention it one more time. Software training and mentoring are the three things we're responsible for, and we always have our learning, our building expert analysts. So we provide MoldFlow training. So if you are a MoldFlow user and you haven't gone through the fundamentals class, our next class is going to be in May. So contact us if that's something you'd like to go through. We have our Ask the MoldFlow Experts webinar series, which you just observed. We have Moldflow office hours, so if there's ever a topic, a specific topic that you want to just sit down and chat about, sign up for some Moldflow office hours. We'd be happy to have those conversations with you. And again, all of this information can be found on our website, and follow us on LinkedIn as well. So when you want to know when these webinars are going to be or whatever it may be, Moldflow related, there's often good information to see on LinkedIn. So with that, we are going to have a Q&A session. I'm going to open up the mics. Okay, so first raise your hand, and I'm going to open up your mic if you have a question. I do have one question that was submitted in the questions section. You can also submit a question there. So it says CRIMS data is often not available. So are there workarounds, or how do we obtain that? That's a great question, and we deal with this all the time. And it goes back to talking about the best use of Moldflow. When I started my career in Moldflow 29 years ago, a lot of the work I did was, we'll call them fixer-uppers, right? The mold was built, parts were being made, there was some issue. What can we do in Moldflow to fix it, right? And one of those was Warpage. But when you get to that point, it's almost too late for a couple of reasons. One, the mold's built, right? So the best fix may be a part design change, or it may be a gate change, or maybe a cooling line change. Once the mold's built, that's a very difficult thing to go back and change. So, over the years, we've preached doing Moldflow well in advance. And those are the cases where we have the best success stories, because we're able to avoid those problems in the first place. And part of that process is getting good material data, right? I mentioned that. But if we're waiting to the last minute where we're building molds and it's all rush at that point, we're ready to go, getting good material data, if it's not in the database, can be a problem. It can be a 4 to 6 week timeline. And of course, there's always the question of who's going to pay for it. So it's not something that can be done quickly. So it behooves us to start this process much earlier. But that doesn't mean you can't do Moldflow analysis. You just can't, you have to lower your expectations on the results, right? If you're going to pick a substitute material, we have to do that judiciously. We have to pick a material that is as close to the real material as possible. So there's some ways to do that. I won't get into the nitty-gritty detail here, but then we have to rely more on a trend analysis, saying, okay, maybe we don't believe the magnitudes, but we can believe the trends. So there's no real workaround. It really depends on what your goals are, how accurate you want the results to be, and what you're trying to achieve. Okay. Next question I see is, so if CRIMS information is available, the suggested mesh for the analysis is dual domain, and if it is not, it's better to use 3D mesh for the analysis. So there are a lot of factors that go into determining which mesh is best, okay? I mentioned the 3 different mesh types: midplane, dual domain, and 3D. Midplane and dual domain rely on CRIMS data. Dual domain can't pick up buckling, for example. There is no buckling analysis in dual domain. So we rely on midplane. I found over the years that midplane analysis tends to be the most accurate, even though the mesh itself and the results look a little choppier, so to speak, if that's a good way to describe it. But there's a whole long conversation that goes on, that needs to go on, when we talk about the differences in the different types of mesh. 3D meshes do not rely on CRIMS data. Moldflow developers are working on a version of that that's going to be hopefully coming out at some point. There's no promises, of course, along those lines. If there were, they would probably have it out in the software now. But suffice it to say that, again, it's really up to the analyst on an individual basis, case by case basis, to determine which mesh is the best. And so they better be well trained on understanding what the strengths and weaknesses of each mesh type are. Okay, next question. Can shrink simulation be trusted in 3D and mid-plane? So when we talk about shrink simulation, so there is an algorithm in MolFlow, and I'm assuming this is the algorithm this particular gentleman is talking about, that can predict shrinkage in each direction, in fact. So, you know, if we have CRIMS data and if we have all the inputs that we can expect to match very well at the press, then I think the shrinkage values that are calculated in MolFlow can be trusted. I would say in mid-plane, generally speaking, more so than 3D. But again, you know, we got to be careful. Do we have good material data? Can we expect that all of the variables, you know, like lot-to-lot variation, you know, leaky check rings, whatever, all the slop we call it in injection molding, to the degree that those things can be controlled, I think we can trust the shrinkage values we get out of MolFlow. But I always like to temper them with, you know, I like to look at the CRIMS data. You know, the CRIMS data is tested over a range of different process settings, for example, different wall thicknesses. I like to go to the material supplier and see what they know about the shrinkage of their material. So shrinkage can be a touchy situation, and I think it is wise to go to various sources to land on a final shrinkage amount. And again, if we do a good job with part design and we do a good job with mold design, then we can expect to have a larger processing window. And with larger processing window, right, we can likely be able to change the amount of pack pressure we have to affect the final shrinkage value. So if you need to dial in the size of your part, you know, a little bit here and there to match the shrinkage that was cut to the steel, you better have done a good job with your part design and mold design to be able to do that at the press. Follow up to that was, can sink be predicted? Yes, sink can be predicted in 3D and mid-plane. Sorry, I'm trying to my window to work here. Any other questions? Francisco, I'm going to open up your mic here, so bear with me. Let me see if I can get this to work. Okay, Francisco, unmute yourself and then ask your question. Francisco, are you there?
Can you hear me now?
Yes, I can hear you.
Okay, I was struggling with the microphone, but now it's okay. Yeah, thank you very much for the presentation, and I agree in your comments that every part is different, even in the way that many years of working in the MolFlow, we are still at some point surprising of the result that we obtain. But in regards of the Warpage, I think that my main question here is, so in your experience, if you want to rely about one common requirement in our plastic components is the flatness level, right?
Mm-hmm.
So if you are going to drive to get the goal of this flatness level, to understand if your part will achieve the value or if you need to perform some modification in the part design, then once again, you follow your strategy first with one specific mesh, or imagine that you have the part already optimized. Which result for you is more confident, the mid-plane, the dual domain, of the 3D mesh?
Like I said before, I tend to, and it varies depending on the part design, right? The type of the part.
Mm-hmm.
If we have thicker, chunkier parts, then 3D is the way to go. But generally speaking, mid-plane is the one I tend to rely on.
Okay.
Okay, and again, it requires solid material data, right? Good CRIMS data, juncture loss data, the whole 9 yards, making sure that we have very good material data.
Exactly, and I also agree in your comment because I already performed a simulation when I can see big difference in values between the dual domain and the 3D mesh. However, the trend is exactly the same. So I think this is a really good advice.
Yeah, that tends to be the case. Is the trends among the 3 different mesh types tend to match, assuming buckling is out of the equation among the 3. Yeah, so the trends tend to match. The magnitudes not necessarily.
Correct. Okay. Thank you very much.
You're welcome. Brad, I see you have a question here. Let me try to unmute you. I think you're unmuted. Try to unmute yourself. Brad Shanowski. All right, looks like you're unmuted, Brad. Go ahead.
Can you hear me?
Yep, I got you.
Okay, so the question was, I see sync, I'm seeing large differences between mid-plane and 3D. Are they both, like, how can you get such different results, and is one of them more reliable than the other as far as shrink prediction?
Yeah, so Molflow has made some
sync prediction. I'm sorry, sync prediction.
Yeah, I understand. So Molflow has made some efforts over the last couple of revisions to try to get the two to agree between the midplane and dual domain, or midplane and 3D rather. So there may be cases where that's not going to match. And I'd have to see the meshes you're doing on the 3D to tell whether or not, sometimes it's mesh related in 3D, whether or not you're going to get good results. And also, are you on the most recent version of Molflow? So if you're several versions down level, then you will likely see greater variation between midplane and 3D when it comes to sync marks.
So they should be the same provided the mesh is good. Is that what I'm getting?
They're not always going to be. That is a known thing in Molflow, that generally speaking, there's going to be some differences. So probably best to rely more on trend analysis there.
Yeah.
You know, if I change the rib thickness by X amount, how much improvement do I get in sync mark results, that kind of thing. And generally speaking, you know, with a midplane type of analysis, we're targeting about 0.1 millimeters in a sync mark result to try to keep that at bay.
Right. May I ask another question?
Sure.
How do you know when you want to use buckling analysis?
The answer to that is always.
Oh.
So, you know, and most parts aren't going to buckle, but it's those ones that do and you miss that are going to bite you. So.
Okay. So you should always look for buckling, and you have to run mid-plane to do that, correct?
3D will run it as well.
But is there any problem with the prediction with 3D with regards to buckling in, say, glass-filled parts?
Not that I'm aware of. I will warn you, it will take you a very long time to run that analysis.
Okay, thank you.
Mm-hmm. Okay, we got Daryl. Daryl, you want to ask a question? Go ahead and unmute yourself.
Yeah, I just was curious when I'm thinking about who we can use to try to do the analyses when it comes to looking at the mold designs, whether as you're proposing this review that you've shown, you're modeling the water and the gating and all that in Moldflow, or whether you're importing from the mold designer, the layout that they have, and then utilizing that.
Yeah, so it's all goes back to timing, right? You know, generally speaking, when we're laying gates out, we're not really figuring out the cooling at that point. We can't figure out the cooling at that point because cooling has to get around gating runners and so forth. So we're making an assumption early on that the cooling is uniform. Okay, so and we can guess at a good cooling design, right? As mold flow analysts, we ought to have a pretty good idea what makes a good cooling design, but it isn't something that's necessarily going to be able to be implemented in a given tool. So we have to rely on the mold maker to supply us with that mold design initially before we can run cooling analysis. So it's important to involve the mold maker early on in the process. If you're going to do mold flow early, involve the mold maker. Source your tooling early and get the mold maker involved so we can try to get that implemented as quickly as we can.
Makes sense. Thank you.
Mm-hmm. Chris, looks like you have a question. Go ahead and unmute yourself. Chris Hempsel. Chris, you there? Okay. Not sure that Chris either is able to get himself unmuted or not. And that exhausts all the questions we have in the question section. So we'll end it there. If you guys have any other questions you think of offline or whatever, feel free to shoot me an email. My email is tim@caservices.com, as you can see here. And again, feel free to visit our website for any other information. So yeah, you can also call us at this phone number. So want to thank you all for attending. This is an important topic. Look for other important topics down the road with our Ask the Mold Flow Experts webinar series. And hope you enjoy the rest of your day and hope to see you soon. Take care.